Okay, just one day of 2-7. Last lesson of chapter 2. Topic is the inverse. Okay. For the most part, let's see, you can assume every function has one. We'll work a little bit on finding a function's inverse. Work a little bit on notation. First of all, just like a heads up. If you ever see that f to the negative 1, that would be referring to whatever function was f, that's its inverse, okay? Graphically, it's a reflection over the line y equals x, okay? We'll see that on the next slide. Here's really the way I want you to think about them. We go back to a mapping diagram. And now I'm going to get specific. I'm going to call this circle not just x values. I'm going to call it the domain of function f, which you're probably thinking, yeah, domain always goes with the x value, so duh. Here's the range. The way in which numbers in the domain are paired to numbers in the range is the function itself. It says how the numbers should be paired together, okay? Let's go the opposite way. The function, it's still going to pair the numbers together. It'll pair the same two numbers together. They just switch, okay? So now there's like this reversal that over here, what was the range of f is now the domain of f inverse. The domain of f is now the range of f inverse, okay? You can think about it like just everything kind of just switches. That's more or less what happens, okay? Again, we're not getting into any specifics. This is more just big picture. This is what conceptually is going on with the inverse, okay? It switches everything. Instead of a function that takes x, like you put in x and you get y as your answer, if you instead wanted, like the function is kind of the same context. The problem is about the same thing, but you want to put in the y value as your x, if that makes any sense, right? Let's say your input, put the y in as your input, and then your answer is the x. That's what an inverse would do, okay? Conceptually, that's what it does. Let's look a little closer at a specific one, okay? Now, first things first here over on my graph, we talked about this line over y equals x. I'm going to put that on here. Okay. So here's how I would go about graphing the inverse. I'm going to make a table. Well, no. Well, okay. This is going to get weird. I'm going to kind of make a table. I don't really want it for this graph. I'm going to want it for the next one. So it's a line, right? A good one for us to look at. But let's graph it like we do every other line. So I'll go down to -3. Then I'm going to use its slope of up 2 and over 1. Whoops, I got to back up. Put the y-intercept at -2. Should be at -3. That blue one I just colored over. should have been down here. There we go. Second point should be there. Little squiggle there on my line, but whatever, not too bad. We'll call it a line. Okay, so typically we'd say that's good, right? That'll be sufficient for drawing a line. Now, why do I want to go backwards and get its table? Well, you'll see. Right now I'm just making the points of the line y equals x a little bit more clear, because I told you on the slide before that the inverse function, which that's kind of what's left for this problem, is to get this line's inverse. You should see that it's reflected over that line, okay? So here's how I would go about this. Is I'm going through and taking a look at the points that I plotted, and I'm now putting them in my table. Right now, if our point was to just graph this line, obviously we wouldn't do that, where it's like you're putting together a table of values, right? But usually we would use the table to make the graph, and we already have the graph. Really, I want this table to help me out with the inverse, which I'm going to graph next. So -1, -5, that was on there. 0.0, -3. 1, -1. 2, 1, 3, 3, and then way up at the top, I plotted the point 4, 5. Now I'm going to use this table to help me out with F inverse, because I can't do the same thing at the moment, because I don't have an equation for the inverse, okay? In the last part of this problem, we'll get one. I'll show you how that would be done, but at the moment, we don't, okay? But here's what you could do, right? Think back to that mapping diagram on the previous slide, how X and Y switch. They switch roles. Domain versus range, right? The X's become the Y's become the X's. That is, if we make the jump from F to F inverse. So one thing I can do is the table I just made, I can go point by point, and I can just flip-flop X and Y. And now I got a table of values that I could graph my inverse, okay? If you don't have the equation, this would really work for any inverse graph that you wanted to produce, right? Because I'm doing it in kind of an interesting way that I actually don't have an equation that is the function of F inverse. And you could make one where you really don't know how. Again, I'll show you the basics of how to get one in a minute. But that's still, if it's a more complicated function, that might be really hard to do. Okay, but this will work just fine. 5 over, 1 down. -3, 0. Excuse me, -1, 1. Whoops, I was going to say. Getting to the point right here, and I was getting ready to graph it. I'm like, this is not working. Like the next point's not falling where it should be, sure enough, right? One, 2 is definitely where it should go. 3, 3. and 5 by 4. Okay? All the points, the x and y coordinates would need to be switched. Again, that's why I was stuck there for a second at the point 1, 2, because I didn't switch them, and it was 2, 1, and I was like, that's not following the pattern. Okay, and by the way, just for some labels on here, I do have the line y equals x that hopefully you see that, yeah, that's a reflection, right? If you kind of look at it diagonally, they're a mirror image on either side. The blue one, we'll call that one f, and the red one that I just made from switching all the points, that is indeed f inverse. Okay, so I got a table of values. I've got a graph for it. Now, I suppose if we got fancy with just because it's linear, we could take a couple points. We could find the slope, use point-slope form, and find the equation, right? Especially in light of the table. We've practiced that in a couple different chapters. That if we're talking linear, and you give me 2 points on the line, I can find the equation that goes through those 2 points. Not only do we have 2 points in our table, we have 6. So we could pull it off. But here is typically how you would find an inverse. And this would be more broad than just linear. I would switch x and y. And then solve for y. So I'm going off of this right here, the original for f, right? X equals 2y minus 3. Notice it still fits that same theme of x and y switching, okay? Now that by itself, that's not the inverse function, right? That's the original function f with x and y switched. That's not what we're looking for. I got to do the second part that once I have that, I got to solve for y, which if the function's linear, it's not so bad. Add 3. And that would leave you with that. X plus 3 equals 2y. Which would be 1/2, both of those parts, the x and the 3 need to get divided by 2. So I have 1/2 x plus 3 over 2, okay? Now, if I compare that to my graph, right, sure enough, in terms of the slope, yeah, it over 2, up 1, it definitely has a slope of 1/2. And then right here, checking out my y-intercept, it looks to be halfway in between 1 and 2, or 1.5, which as a fraction would be 3 over 2, right? So it does all look consistent that our table, our graph, and now the equation that we found, they're all correct, okay? But again, this is a real general way. If you're just doing some algebra, whatever equation you had, you could do that. Switch x and y, solve for y. The end result, once y is solved for, the original function that you started with, you've then got its inverse, okay? We'll call it quits there, and there you go. That's the last lesson for Chapter 2.